Hello, everyone, and welcome again to iTelescope and our webinar. And my name is Christian Sasser. I'm the astronomer in charge for iTelescope, and I'm very pleased once again to welcome Dr. Deanna Hooper, University of Helsinki. This is her third time, and this time she's finally going to touch on her favorite subject, that is the cosmic microwave background, and we can't wait to hear about it. I'm so excited because this is just probably one of the most exciting topics that you can find. So, Deanna, Dr. Deanna Hooper, straight over to you. Welcome.
Yeah, thanks for having me back. It's amazing to be back. It's my fourth time here now, actually, I believe, because we did two the first year. Then I'm coming back every January and February, so this is my fourth time. And today we get to do my favorite topic. Love it. I'm really excited about this.
Wonderful. So we can't wait. Let's get going. Thank you. And we've also got two poll questions, so just remind me when you want them launched, please. Thank you.
I think it's good to do the polls at the beginning, actually. Like we can start with the polls before I get to the slides.
Okay, so I'm going to start with the obvious one first. Yes, and let's launch this one here. So this one was when the cosmic microwave background was first measured, what did people think it was? Was it light from a distant galaxy? They knew what it was. Pigeon dropping, that's good. Yes. Or aliens. Well, what was it? Yeah, it's a very, you know, from an engineering point of view, Deanna, this is one of the most exciting things that ever happened. It's just so incredible.
Yeah, I am going to definitely go into detail about how this discovery took place and what it means. But I think the answer to this question is going to surprise most of you. It's very clickbaity. Like, you will not expect the answer to this question.
You will not expect the answer to this question. Let's see. We got to give it a few more seconds, and then, yeah, just give me 10, 20 more seconds. I can see the answers. You probably cannot, but I see them evolve at the moment. So I won't comment. I'm going to leave it all up to you. Okay.
Yeah, give it a few seconds. Once everyone's
okay, I'll
done
give it a few more seconds. Don't be afraid to vote, please.
Just going to say hi to Paul in the chat here. It's great to see you here, Paul. Paul's one of the regulars on my own show, so it's great to see him here as well.
Okay, very good, very good. Okay, I'm going to share the results now.
I feel like a lot of you might have already known the answer to this question. So it is indeed pigeon droppings, which is very, very fun. I do appreciate the two of you who selected aliens. I love that you did that. It was not aliens this time. But when the CMB, the Cosmic Microwave Background, was first measured, people thought it was actually pigeon droppings. And I'll tell you about that in a bit. But yes, they did not know what it was. They did think it was pigeon droppings. Okay.
Great.
Let's run the second poll.
I'll go the second one. I'm going to launch it now. Wait a minute. Stop. I first have to say stop sharing that one. I think otherwise I can't launch the other one. Just 1 second. Okay, here we go. So what does the cosmic microwave background tell us? Oh, I was just discussing this with Deanna. I won't comment on this. So is it the components of the universe, the shape of the universe, the future of the universe, when the first stars were formed? That's
and this one is multiple choice, so please select all of the ones that you think are correct.
Yes, that's important. So you can, it's definitely multiple choice. Yeah, that's a good one. It's a very good one.
And I feel like this is a slightly trick question.
She always gives us something to think of. So watch out, watch out. That's all I can tell you. Yeah, that's getting a lot of responses. Interesting here.
I think there are perhaps one or two of these that are obvious yes/nos and two that are maybes. So let's see what people say to this. Okay,
I'm going to give it a few more seconds. Don't be afraid to vote, please.
Yeah, don't worry. This is not an exam. You are not being tested. This is just because this one will set the scene nicely for the second half of my talk.
Right. Okay, I'm going to end and share. Please comment.
Okay, so 34 of you selected components of the universe. This is correct. We can learn about the components of the universe. 43 of you selected shape of the universe. This is also correct. We can learn about the shape of the universe with the CMB. 28 of you selected the future of the universe, and this one is actually not true. The CMB can give us ideas and estimates, but it cannot tell us how the universe is going to end. And 30 of you said when the first stars were formed, and that is also correct, which sometimes seems a bit counterintuitive because the CMB and stars don't really seem like they go together, but they do, and I'm going to tell you why in the second part of the talk.
Excellent. Thank you. That was a great start. So, okay, thanks everyone, and let's get going.
Let's get going. Bring up slides. Okay, let me know if there's any issues with how it looks, but otherwise I'm going to assume you can see me all well. Right, so today I get to tell you about one of my favorite things in the universe, which is the cosmic microwave background radiation. I love talking about this topic, and hopefully by the end of this webinar, I have no idea how long I'm going to talk for. It should be about an hour, but hopefully by the end I'll convince you why the CMB, the cosmic microwave background, is the most amazing thing in the cosmos. And I came up with a kind of weird title, and then Christian proposed this better title of The Dawn of Light, and I love this title. So this is what we're going to go for. So what I'm talking about today, cosmic microwave background, is basically the first light in the universe. So the very first dawn in the universe. So let's jump straight into it. CMB, the cosmic microwave background radiation, is, in my opinion, the greatest discovery in cosmology. And I'm not the only one who thinks this. There have been several prizes and awards given for the discovery and the predictions of the cosmic microwave background radiation. In 1974, there was a Nobel Prize awarded to Penzias and Wilson for the first measurements of the cosmic microwave background radiation. So first Nobel Prize. In 2006, there was a second Nobel Prize given to the COBE team for measuring tiny, tiny temperature differences in the cosmic microwave background. I'm going to tell you what all of this means, don't worry. Then in 2018, there was the Gruber Cosmology Prize, which is perhaps not as well known as the Nobel Prize, but is considered equally important. It's given yearly to major discoveries. And the Gruber Prize in Cosmology went to the Planck team for creating the most precise map ever of the cosmic microwave background radiation. And I wanted to add a fourth prize here because there's a nice little box in the right-hand corner, but there's only 3 to add. But also anyone who's ever met me or has let me talk for more than 2 minutes knows that I will always tell you that the CMB, the cosmic microwave background radiation, is the holy grail of cosmology. It is the most amazing thing we've ever been able to measure. And I consider this quote from me to be as equally important as the Nobel Prizes, and I needed something to fill this slide. So you get a quote from me about how amazing the CMB is. Okay, so why the prizes? Why the hype? What does this all mean? What are we actually doing here? Like, why am I telling you about the cosmic microwave background radiation? So that's the first part of my talk, is going to be answering the question of how did we get here, which is, of course, a pretty big question to answer. So let me go back to the very beginning, and I mean like the very, very, very beginning here. So I want to take us back to the dawn of time and the universe itself. I want to take us back to the Big Bang. I'm not sure, can you just confirm if you can read the text on the top of the slides? Because for me, it's slightly cut off.
Yes, it says our best body of the history, model, sorry, our best model. Yes, yes.
Then it's only cut off for me, so that's fine. I don't need to see it. Okay, so the best model of the history of the universe that we have is the Big Bang model. So what you can see here is a sketch of the history of the universe, starting with this big thing on the left, which we don't really know what it is. It's the beginning of everything. Then we have this period where the universe grows dramatically. Then it keeps expanding a bit more slowly. Stars begin to form, stuff happens, galaxies form, reappear. And at some point, the universe starts expanding again. So the expansion is getting faster than it was in the past. What this means is that the universe is growing. It has been growing as long as we know, and it is growing now faster than it was in the past. So this is the Big Bang model. But this is not the only model we've had of the universe. There have been other ideas and other theories and versions of what the universe could look like. In the early 20th century, a very popular model is what is known as the steady state system. In the steady state model, the universe has always existed and will always exist. It's unchanging. It's something that is always going to be there. In which case, asking the question of how did the universe begin, how is it going to end, wouldn't make sense. Because the answer to that would be, it's just always has been here, always will be here. So that was the steady state model. And the Big Bang model is this idea that the universe used to be a lot smaller and a lot hotter, and it gradually expanded, got a lot bigger, and cooled down. We have a clear starting point, and we can map the history of the universe into the future. So in the early 20th century, we had these two competing ideas, the steady state model and the Big Bang model. And both of these make specific predictions, specific observations that they say, like, if my model is correct, this is what you should see in the universe. What I'm going to be talking about today is, of course, one of the biggest predictions of the Big Bang model. So in 1948, three physicists, George Gamow, Ralph Alpher, and Robert Herman, were working on this Big Bang model. And they predicted that in the Big Bang model, at the back of the universe, behind everything else, behind the stars, behind the galaxies, if you take everything else away, right at the background, there should still be a residue light, light that you cannot get rid of everywhere in the universe. So where would this light come from? So in the early universe, there are three main components. You have protons, which I'm showing here as red circles. You have electrons, which I'm showing as blue circles. And you have photons, which are particles of light, which you can see on the right as these little yellow circles. Now, just to comment, these colors are not real, these sizes are not real. We know they're not actually spheres. This is just to give you the standard picture of particles. So three main particles: photons, protons, and electrons. Photons are particles of light. Now, in the early universe, everything was really, really, really hot. So all of these particles behaved as a dense gas. They were constantly bumping into each other. The protons were bumping into the electrons and the photons were bumping into each other. This meant that light couldn't actually travel, because anytime light tried to move anywhere, it would hit another particle and bounce off. So the universe was opaque. You couldn't see through it. It was this like big, thick smog. Now, as the universe cooled down, a very cool thing happens, and that is that protons and electrons can combine together to form the very first hydrogen atoms. Protons are positively charged, electrons are negatively charged. These can come together and form the very, very first hydrogen atoms. At this point, once protons and electrons are coming together, again, atoms are not spheres. This is just to make it kind of easy to visualize. Once protons and electrons have combined together to form these atoms, the photons can now travel freely. You can imagine that instead of having this thick gas, the protons and the electrons are now bound together in atoms. This means that photons, particles of light, can actually start traveling freely. They're no longer bumping into things. So about 380,000 years into the universe, protons and electrons combine together and the particles of light break away, and these start traveling freely throughout the universe. These photons have been traveling ever since. As the universe is expanding in the Big Bang model, universe is expanding. So the wavelength of these photons, because every particle has a wavelength associated to it, so the wavelength stretches. This means the energy shifts, and it shifts into the microwave range of the electromagnetic spectrum. If we consider the electromagnetic spectrum, which is like everything you see in light, you can have very high energy gamma rays, and you can have like very low energy microwaves on the other side. In the middle, you have the visible things that we can see. You have radio waves, which are slightly less energetic than what we can see. And even less energetic than radio waves, you have microwaves. So the idea is that you have these particles of light, broke away 380,000 years after the beginning of the universe. They've been traveling freely ever since, and now they've been redshifted to microwave frequencies. So we have background light that is everywhere in the cosmos, and that is in microwave frequencies. And for once, physicists gave something a reasonable name, and they called this the Cosmic Microwave Background Radiation. The radiation that is in the cosmos at the background in the microwave frequency. That is what the CMB is, Cosmic Microwave Background Radiation. Another prediction that the Big Bang model makes is that this background light should be a black body. And this is a bit counterintuitive to describe light as a black body. So a black body is something that emits light at all frequencies. So every possible frequency. If you consider a light bulb or your car light or anything like this, any artificial light usually only emits at specific frequencies. Whereas the light that is in the Cosmic Microwave Background Radiation emits at every possible frequency. So within the Big Bang model, we have these two predictions. there should be this background light everywhere in the universe, and it should be a perfect black body, or at least very close to a perfect black body. I'm going to make a caveat on the black body later on, but for now, let's think about it as a perfect black body. Then, just going to make the comment here that later on in the 70s, people realized that this black background radiation couldn't be completely at the same temperature, because that would say that the universe is completely smooth. But we know the universe isn't smooth because we have galaxies. So in the 70s, people said that if this CMB is there, it shouldn't be a perfect temperature. It should have some tiny temperature differences. These tiny temperature differences explain how galaxies exist. So we have several predictions here. We have all of these different predictions. So 1948, steady state model, Big Bang model, still competing. Physicists working on the Big Bang model make this series of predictions about the cosmic background radiation. Okay, let's fast forward to 1964. 1964, we have two astronomers, Penzias and Wilson, and these two were working on the Horn antenna data. So the Horn antenna is this massive structure that you can see here. This is a 6-meter long radio telescope. So it's shaped like a horn, which is why it's called the Horn antenna. You can see Penzias and Wilson down here below. I guess you can see my mouse. You can see them down here staring at the experiments. The purpose of this antenna was to measure radio waves bouncing off of satellites. They were kind of pioneering communication technology. So this is the purpose of the Horn antenna. So just going to make a comment here, though. When I advertised this talk, someone replied to me giving the backstory of Penzias. And Penzias actually has a really interesting backstory. He was a Jewish boy who escaped Nazi Germany just basically on the eve of World War II. And his family were only able to get out of Germany because of a random act of kindness by a complete stranger. So there's this really interesting backstory to Penzias. I'm not going to talk about it now, but I really encourage you all to check it out because it's a really interesting story. So Penzias and Wilson are working on their Horn antenna data. In order to do the measurements they want to do, they need complete clean signals. So they need to get rid of everything else. They need to remove our galaxy. They need to remove the sun. They need to remove everything from their data that is producing noise. So they did that. They got rid of everything. And then at the background, there was a signal that they could not get rid of. There was a background glow in their radio telescope. There was some light or something that seemed to be emitting at a temperature or having a temperature of about 3 degrees Kelvin, which is minus 270 degrees Celsius, minus 454 degrees Fahrenheit. And whatever they tried, they could not get rid of this backlight. Now, at this point, Penzias and Wilson knew, okay, this cannot be from our galaxy because this is everywhere. It cannot be from the sun. It cannot be from Earth because then it would only be in one place. But they could see this everywhere. So then they went and looked at their telescope and realized that there were pigeons nesting inside the telescope, inside the Horn antenna. These pigeons did have a nest inside and there were pigeon droppings. And Penzias and Wilson thought, these pigeons are to blame. So this goes back to the poll question of what did they first think it was? And they first blamed these pigeons. So then they got rid of the pigeon nest, they cleaned the antenna, they took the data again, they went back and they still had this background noise, which was kind of annoying. So Penzias and Wilson did not know that this was a prediction of Big Bang cosmology at that point. Then, they were quite frustrated. They were chatting to a colleague called Burke. And this colleague, when he heard about this, was like, hey, I was just down in Princeton chatting to some guys in Princeton who are working on this. So 1964, down in Princeton, 3 other physicists, Robert Dicke, Jim Peebles, and David Wilkinson, were working on figuring out how measuring the CMB would be a clear proof, so to speak, of the Big Bang model, and how they could go about measuring this. So they were working on basically doing what Penzias and Wilson had accidentally done. So then, after this conversation, Penzias called Dicke down in Princeton and was like, hey, I've heard a rumor that you guys are working on something. Can we chat? So Dicke drove over to where Penzias and Wilson were. They put their notes together and they realized that what Penzias and Wilson had found was indeed the first ever measurement of the cosmic microwave background radiation. There's something very cool that these two teams did, which I think is a very nice thing in science. They decided to publish results together. So the Princeton team put out a paper that said, if you measure this background light, it means the Big Bang is the correct model to describe the universe. And in the same journal, like back to back, Penzias and Wilson put an article saying, hey, look, we've measured this background light at the universe. So the two teams together put out this news, this scientific articles saying, hey, look, we found this prediction of the Big Bang model. So this was kind of the first idea that the Big Bang model is the correct description and that the steady state model did not fit the observations. Because within the steady state model of the universe, you could not explain this background light. So 1964 is kind of the death of the steady state model. This is when Big Bang cosmology was like, this is the correct model. As a reminder from my first slide, later on in 1978, Penzias and Wilson get the Nobel Prize in physics for this discovery. Okay, so we have the first measurement ever of the cosmic microwave background radiation. There's this background glow. Then 1970s, as you might remember from before, people realized that this background glow should have tiny, tiny temperature differences. It's not just at 3 degrees Kelvin, it's 3 degrees Kelvin with a fractional difference of 1 part in 100,000. So for one in 100,000 temperature difference. Okay, 1990s, we jump forward a bit, technology has progressed a bit. NASA launches the COBE satellite. COBE stands for the Cosmic Background Explorer, and COBE was tasked with looking for this cosmic background radiation. It's an amazing telescope. It was sent up, like, go to space where it's quiet, where there's not much noise, and just try to measure the microwaves at the background of the universe. 1990, which is not that long ago. This is only 34 years ago. Okay, 1992, COBE releases the first image ever of the cosmic microwave background radiation. And this is what they released. So this is when you take away the galaxy, you take away the stars, you take away everything else, and you just look at what's left, and you get this. The blue, the pink here represent different temperatures. So you can see there's blue blobs, which are slightly colder. You can see purple blobs, these like reddish purple ones that are slightly hotter. Tiny, tiny differences. We're talking about a fraction of a fraction of a fraction of a degree. Really tiny differences. But COBE measured this. And what this is showing us is this background light is real. And the tiny temperature differences that we predicted are real. We can use the CMB to explain why we have galaxies. 1992, COBE produces this map. Again, the COBE team went on to win the Nobel Prize in 2006. But I just want to go back and show you COBE satellite again. There's one of the instruments that you can see, I think it's this one here, this little guy poking out here, that looks like a little robot with eyes. This is a specific instrument on board COBE, which is called FIRAS, Far Infrared Absolute Spectrophotometer. FIRAS had one job, which was to measure if the CMB was a black body. So I mentioned before that one prediction from Big Bang was that the CMB should be a black body. So what you see here is the plot that they produce. So you have the intensity here and you have the frequency. So this is kind of measuring what a black body should look like. What you see in blue is the theoretical prediction of what a perfect black body would look like. The red dots, the red crosses are the COBE data. This is an incredible match. You see the blue line goes through the data points perfectly. This here showed that the CMB is the most precise black body ever measured. This was a clear prediction of Big Bang cosmology, and here it was. We have the temperature differences, we have the precise black body. We found what the Big Bang model predicted. Excellent success. Perfect. COBE got the COBE team, the COBE FIRAS team got the Nobel Prize, well deserved. But that's not the end of the story, because physicists love pushing things and going further and seeing what else we can do. So then, in 1997, there was an incredible experiment, because people decided, like, what if, instead of measuring the whole sky, we just stare very, very, very intensely at a small patch of the sky? The reason you do this is that you can get better precision. In order to map the whole sky, you need kind of a wider lens. In order to stare deeply at something, you need good resolution. So you can sacrifice on how much you see in order to gain how deeply you can see. It's either wide vision or narrow vision that is very focused. So in 1997, there was the BoomeRanG experiment. And I love this experiment. They built a little microwave detector. They put it on a balloon and sent this balloon into the polar vortex above the Antarctica. What happens here is that the balloon gets caught up in a wind stream and it spends 2 weeks just going in circles above the polar vortex and then comes back down like a boomerang. So they threw this balloon up, let it circle for 2 weeks, brought it back down. They did this 3 times. And just a fun fact, they then kind of engineered a name for it. So they called it BoomeRanG because it goes and does a loop. But BoomeRanG is actually an acronym. And I had to write it down because I never remember it. BoomeRanG is an acronym for Balloon Observations of Millimetric Extragalactic Radiation and Geophysics. This is how physicists name things. They engineer an acronym and then try to figure out what words they can use to make the acronym work. But the BoomeRanG experiment, which you can see here on the left, launched, didn't launch, it went, did a few loops around the Antarctica, came back and gave us this picture down in the bottom right. And what this shows us is that these temperature differences are a lot more precise than what COBE measured. COBE gave us this nice blue, purple, pink map with large splodges. BoomeRanG showed us that we could do better. Now imagine if we could get this map, but for the whole sky, this level of precision across the entire sky. This would be an incredible achievement. And the reason we want to do this, partly because we can, but also, just to recap here, this light that we're taking photos of was produced 380,000 years after the Big Bang. These maps are pictures of what the universe looked like 14 or 13.5 billion years ago. If we can get a photo of the baby universe, it tells us so much. And of course, getting blurry photos is good. But imagine if you could get such a precise photo that you could look at the baby universe and say, like, I see what you did here. I see exactly what you did here. I know what the universe looked like then, and therefore I know what the universe looks like today. You get this baby photo, you can figure everything out. So once COBE had shown we can do this, BoomeRanG was like, we can do this better. 2001, NASA launches WMAP. WMAP is the Wilkinson Microwave Anisotropy Probe. This launched in 2001 with the mission of seeing if it could actually get this BoomeRanG-style level of precision across the entire sky. You have a photo of the launch here on the right and what WMAP actually looked like on the left. WMAP took data for many years. They had several data releases, several maps, one after 3 years, one after 6 years, and one after 9 years. So I'm going to show you the final WMAP release, which is this one here. And by now, we're getting incredibly good precision. You know, you can now see there's these blue regions, there's these green regions, there's these orange regions. All of these are tiny, tiny, tiny temperature differences. Again, we're talking about something that is a fraction of a degree. So we're saying here that this blue region might be 3 degrees or 2.7 degrees, and one of the orange regions is 2.7000001 degree. This is a tiny, tiny, tiny difference. But this is showing us how these particles of light behaved in the early universe. We know that the warmer spots and the colder spots tell us why there are galaxies and tell us why the universe looks the way it does. So getting this level of precision was incredible. WMAP showed us, like, look, this is what we can do. At this point, the European Space Agency decided to join the game as well. And they were like, okay, you know, WMAP is amazing. What if we did better? What if we improve this? How far can we push this? 2009, the Planck satellite launches. The Planck satellite had one mission: get the best map of the baby universe ever. So you can see Planck here on the right and on the left, the launch. There was a cool fact about the launch. It was actually launched together with another satellite, the Herschel telescope. Rather than doing 2 rocket launches, they put them both on the same rocket. So they actually both shared the launch pad. You can't really make it out here, but there's this like black label at the top of the rocket, and it's got a picture of Planck and Herschel on it. So they actually launched together, which I'm not sure if there's ever been another cosmology experiment sharing the launch pad, but Planck and Herschel did. Planck satellite took data for 6 or 7 years. There were several data releases. There was the 2013 one, the 2015 one, and the one that should have been 2017 got delayed to 2018. Okay, let's go to July 2018, which, you know, was only 6 years ago. I was working on the Planck data at the time, and we get this map. This here is the most precise photo we have ever taken of the baby universe. This map here is what happens when we turn back our telescopes, turn back 13.5 billion years of cosmic evolution, and ask the universe, what did you look like 13.5 billion years ago? And this is the answer the universe gives us. Here we have these tiny, tiny blue spots, these tiny orange spots. This is showing us that we can break the sky into thousands of tiny, tiny parts, and we can measure the background temperature. We can see that this part here is blue, this part here is orange, this part here is cold, this part here is hot. We got this map. And I know right now you might be thinking, okay, you know, it's just blue and orange splotches. What does this tell us? I'm going to tell you in a minute. But before I jump into what this tells us, I just want to take a minute and reflect on this map. It took 30 years between the first observation to get this map. That is not a long time. In only 30 years, we progressed from the COBE First blue and purple splotch to this map here. This is incredible when you think about it. And in fact, you can see how much it changed over the 30 years. Just take a small patch of the sky. You can see what the COBE map looked like on the far left, WMAP in the middle, Planck on the right. The difference between COBE and WMAP was already a huge achievement. But then from WMAP to Planck, it's another incredible improvement. The precision that we have now with Planck cannot be understated. And this is 30 years, only 30 years. We went from having, okay, you know, there's a bit of a temperature difference, so look how precisely we can measure the temperature difference. And I think this is amazing to think about how much this progressed in just 30 years. And it's not that long ago, you know, early 90s COBE launches, and now we have this Planck data. It's really cool to think about it. But okay, yeah, you're probably still wondering at this point, like, okay, why should I care? It's a pretty picture. It's blue, it's orange, yes, it's very pretty. So this was just the history part. Now I want to take a minute to answer the question of what does this tell us? So this map here is really, really pretty. But this is not how we do science, just by looking at this map. But what you can do is you can take the fingerprint of this map. So you can count how many blue photons there are, how many orange ones there are, and on what sizes. So if I divide the sky into 4, what do I get? If I divide the sky into 8 chunks, what do I get? If I divide the sky into 32 chunks, what do I get? And you can ask this question up to like 2,000 chunks, what do I get? And you do that and you take what is known as the spectral decomposition, the spectrum of the CMB. So just to give you an idea, imagine if you take your favorite painting or your favorite picture, your favorite piece of art or your favorite cat photo, whatever you want, and ask yourself the question of how many pixels in this photo, if you're looking on a screen, how many pixels are blue? How many are orange? How many are green? How many are... Take the whole color spectrum and you can break it down. You can, let's say you go for 10 colors and you group them together like yellows, greens, blues. You could count how many pixels of each color you have on your map. And you could create a graph saying like how many pixels and the colors. So this is exactly what we do with the CMB. We take the fingerprint of the cosmos and we produce this spectrum. So this is the spectral decomposition of the CMB. What you see here on the vertical axis is basically how many splotches of a different size we have. And on the horizontal axis, we have the size. So for an example, this part here on the left, this is about 90 degrees of the sky. So if you divide the sky into 4 chunks, each chunk is going to be about 90 degrees. This puts you here. When you're in this part here, you've divided the sky into many more chunks, and each one of these chunks is about 5 degrees big. When you get to this part here, you're looking at chunks that are 1 degree of the sky. So the whole sky is at 360 degrees. Up here, you're looking at 1 degree in the night sky. By the time you get down to here, you're looking at half a degree in the night sky. And once you get over here, you're looking at a fraction of a degree in the night sky. And this is why we needed so much precision, to get this tail, to be able to go down to this part here. Now, there's something very interesting about this map, which is the error bars. So anytime we do any type of science, we put the data points, which are here in orange, and we put the uncertainty, like our degree of belief. And if you look at these points here, you can see there's these orange points and a big line on them. This is saying the data is probably here, but it could also be here, it could also be down here. It's somewhere on this line. But once you get up to here, you can barely see these vertical lines. I assure you they are still there, but you can barely see them. And when you get to down here, the lines disappear because of the precision we have. So COBE got us as far as this point here. COBE cut off kind of around here, this vertical line that I'm showing. WMAP got us around here. This tail here, this is Planck. This is entirely Planck. Okay, so what do we do with this data? Well, we can run simulations of the universe. So you can create a code. There's several on the market, one in C, one in Fortran. The one in Fortran is called CAM, the one in C is called class. You could minor detail for any coding enthusiasts in the room, but you can use these codes and you run a simulation of the universe. And you ask the question of, if I design a universe with these components and this shape and this history, what would the spectrum look like? And it will split out a blue line. And you do this 1 billion times until you find the blue line that goes through all of these orange data points. And once you have the blue line that goes through all of the data points, you have your best model to describe the universe. This blue line here is extremely sensitive. If you change the components of the universe by a tiny bit, you change this blue line. If you change the age of the universe from 13.82 billion years, which is what we know it to be today, to 13.75 billion years, this blue line changes. If you change the universe from having stars forming at a specific time, you change it by a few thousand years, this blue line changes. So we needed this level of precision with the Planck data, with all the other data, in order to find this blue line as perfectly as we can. But okay, what are the numbers of this blue line? So thanks to Planck, thanks to the CMB missions, we know some things about the universe incredibly well. We know that the universe has 3 components, 3 main ingredients. Everything you see, everything you're accustomed to, everything from me to my coffee mug to the plants I'm surrounded by, all of this is normal matter. Normal matter only accounts for 4.9% of the energy of the observable universe. The second ingredient is dark matter. Dark matter is this type of energy, this type of matter that interacts gravitationally but doesn't interact electromagnetically. This means that dark matter is invisible, but it has presence, it has gravitas, it pulls everything together. Dark matter is what holds galaxies together. It's what gives us actual things in the universe. It's why we have structures in the universe, but it is completely invisible. The third component is dark energy. 68.9% of the energy is dark energy. Dark energy is this weird type of energy that is also invisible and that is pushing the universe outwards and making the expansion of the universe faster today than it was in the past. So thanks to Planck, thanks to the CMB measurements, we know that the universe has 4.9% normal matter. This also means that 95.1% of the universe is invisible to us. And I say I'm a cosmologist, I study the universe, but hey, there's 95% of the universe that we can't see, which is fun. And we need to do our jobs better, but we know that there is 95% of the universe that we can't see. We know there's 26.2% in the form of dark matter. In the COBE days, these numbers were about 70% dark energy, 30% normal matter approximately. In the WMAP days, we were kind of saying like, okay, 5% normal matter, 25% dark matter, about 70% dark energy. In the Planck days, we can add another digit. It's not just 5%, it's 4.9%. It's not 25% dark matter anymore, it's 26.2%. And we know this because of this blue line here. If you change it from 4.9% normal matter to 5% normal matter, your blue line will no longer go through the orange data points. If you change the amount of dark energy, again, your blue line is going to be completely off. If you change any of the components of the universe, you're going to mess this up. So by taking this, which we got from the CMB photos, we know the universe has 3 main ingredients. We know the shape of the universe. The universe is flat. The way we know this is, again, by taking this blue line. So what do I mean by the universe being flat? This is something that often takes a bit to wrap our minds around. Obviously we know the Earth is a sphere. We know a lot of things in the universe have shape. So what does it mean when I say the universe is flat? So we know that the universe looks approximately the same in every direction we look. We can see this on the CMB map. It doesn't matter which chunk of the CMB you take, it looks approximately the same. There's these tiny temperature differences, but whichever chunk you take is approximately the same. The universe looks the same in every direction. And from wherever you look, we do not occupy a privileged place. If someone a few billion light years away did these experiments, they would get the same results. Once you have a universe that looks the same in every direction from wherever you look, there's only 3 possible shapes you can have. You can have a closed sphere, you can have an open universe like a saddle or a Pringle crisp, or you can have a flat universe. So when we say the universe is flat, What we mean is that if you go anywhere in the universe and you draw a triangle, the angles add up to 180 degrees. This is a very unsatisfying explanation, I know. Let's try a different explanation. So imagine you go away from any planet, from any star, from anything with gravity. So you're alone in the universe, there's nothing there. Just you and a football that you took with you. And I mean, for those Americans in the room, I'm talking about a soccer ball. I want a round one, not an egg-shaped ball. Let's take a basketball, which is round in every country. You take a basketball, you go somewhere in the universe, away from stars, away from galaxies, and you just let go of your basketball. In a flat universe, the basketball is going to stay there. In a curved universe, if it's a sphere or if it's open, this basketball will very, very, very slowly move. It will move because of the curvature of the universe. So when we say the universe is flat, what we're saying is if you go away from anything else that you can see, you go away from dark matter, you will still feel a slight force, a slight curvature. But the universe is flat, so you won't feel this. We also know that stars began to form about 400 million years after the Big Bang. Again, if you change this to 500 million or you change this to 200 million, this blue line is different. So the CMB tells us when the first stars began to form. The CMB does not tell us how the universe is going to end. It tells us what has happened in the past. It tells us how the universe went from being in the initial state to how we see it today. It tells us what's inside the universe. And from this, we can make predictions. Okay, the universe is expanding. This expansion is getting faster. This means it's probably unlikely that the universe is going to collapse at some point. But we can't say this for sure. It's probably not going to collapse. But what if dark energy suddenly turns off? Well, then we don't know what's going to happen. We don't expect it to, but we also cannot say that for sure. So my question in the poll was a slight trick question, because I gave you 4 options, and anyone who knows me would have thought the CMB tells us all of these, because that's why Deanna's asking us this. But yes, the CMB tells us about the ingredients of the universe, the history of the universe, the shape of the universe, when stars formed, but it cannot tell us how the universe is going to end. It can show us what it looks like today, and then we can make predictions, but it does not tell us how the universe will end. But the biggest thing that we learn from the cosmic microwave background radiation is that the Big Bang model is the best description we have for the history of the universe. The steady state model no longer works. The Big Bang model gives us a story going through 13.82 billion years of cosmic evolution. I realize I didn't list it on this slide, but obviously the CMB gives us the age of the universe. I mentioned that before as well. It's not written here, but it also gives us the age of the universe. So the Big Bang model tells us that we went from having a slightly smaller, very, very hot universe to having the dramatically big, cold universe that we have today. The Big Bang model tells us how these 13.82 billion years of cosmic evolution happened. And we've also seen, thanks to Big Bang and CMB, that we probably had something in the early universe known as cosmic inflation. Cosmic inflation is this very first point where the universe grows dramatically. If I can go back to this map of the history of the universe, you can see at the beginning, there's like this flash of light, quantum fluctuations, and then boom, inflation happens and you have a universe. So this period of inflation, we don't know much about. But whatever happened during inflation, we know how it ended. Because the way inflation ended sets a starting point for the CMB, for the cosmic microwave background radiation. So by measuring the CMB, even though we can't say exactly, how inflation happened, how long it lasted, what it looked like, what we can say is after inflation, this is what the universe looked like. And thanks to this, we have the CMB and we move forward with it. Without inflation, it's quite hard to explain why the CMB looks the way it does. So while we haven't yet proven inflation and some people are working on alternatives, it's quite hard to explain these temperature differences in the CMB without inflation. So cosmic microwave background radiation, amazing discovery. And it tells us why this picture looks the way it does. Why we say here that the first stars formed about 400 million years after inflation. This period of the dark ages, once the photons were traveling freely, there was no light. The photons have broken away. There's no light in the universe, so we have the dark ages. Then the first stars turned on. What happened when the first stars turned on? They flooded the universe with new light. This new light could bounce off of the photons in the CMB. So this is how we get from the CMB the age of the first stars, because we went from all the light being in the CMB then there's nothing producing light, so we have the dark ages, and then stars turned on, and you feel that flash of energy in the CMB. So by using that, we can use the CMB to figure out when stars formed, because of the stars turning on and adding new light to the universe. Of course, someday, ideally, we should try to understand these dark ages, but for now we just call them dark ages because there's no light, so it's quite hard to measure. Big Bang cosmology tells us 13.82 billion years of evolution, and it predicted the CMB. We've measured the CMB, we've measured the temperature fluctuations, we've measured the black body spectrum. Every prediction about the CMB that was made, we have found. And that is amazing. That is how we do science. This is how science works. You have a theory, you have competing theories, you make predictions, you make your observations, you find which observation matches your predictions, and you adjust your theories based on the evidence. Steady state model could not explain the CMB. Big Bang predicted the CMB. Once we've measured the CMB, there's a logical conclusion. And this is why steady state cosmology is no longer a thing. Okay. I hope by now I convinced you that the cosmic microwave background radiation is amazing. But this is not where the journey ends, because there's more. Not only can it do everything I've already told you, there's more we can do with the CMB. It can't make you coffee yet, maybe someday, but there's more things we can do with the CMB. So up till now, I've been talking about temperature. I focused on the temperature of these photons, the temperature of these particles of light. But every particle of light also has something else apart from temperature. It has a direction in which it vibrates. And this is what is known as polarization. So you can have the polarization of particles of light. And this might sound like a really weird word, but we have polarization in everyday situations. If you put on sunglasses and look through a lake or the ocean, you're more likely to see the bottom than you are without sunglasses. Because the sunglasses are blocking light that travels in a specific direction, you get this polarization. Also, anytime, if you're on a plane or a train and you're trying to be nosy and the person next to you has a laptop, you might have looked over like, what's that person working on? But it's really hard to see the screen because a lot of screens have these screen protectors or filters that is basically a polarized piece of paper. So you put that on your laptop, you can stare at your laptop and see what's happening. But if you move slightly to the side, you no longer see the laptop screen because of polarization. So polarization is just the direction in which the CMB, in which photons in general are vibrating. So the question we can ask, of course, is can we measure the polarization of the CMB photons? And the answer, of course, is yes, or I wouldn't be telling you this. So we can get a second map from the CMB. We can get the polarization map. The one that you can see here is the one we get from Planck. So here, the blue and orange doesn't tell us the temperature. It tells us which direction the photons are vibrating in. So of course, these photons are traveling towards us, but they're a wave. So are they traveling like this, or like this, or like this in a circle? This gives us the polarization. And this gives us this second map here, where we have some polarization in one direction, some in another. You can see people have drawn here these little black arrows on top of it to show you which direction the polarization is moving in. You'll also notice that this is not as precise as the temperature one. This is kind of somewhere in between the COBE WMAP temperature one in terms of precision, but this is Planck. So Planck was designed to measure the temperature. It also did a really good job of the polarization, but that was not its main target. But the very cool thing is everything we did with temperature, we can also do with this polarization map. So you can do the same thing. You can take the polarization spectrum, you can get the data points, and you can draw a blue line through it like we did before. And you can do this separately. You can do temperature and polarization. And this is, I think, one of the things that makes all of these things even better. Because if you take away the temperature and you just look at this polarization map and you ask this polarization map, what does the universe look like? It will tell you the universe has 4.9% dark normal matter, 26% dark matter, 79% dark energy. You will get the same numbers. And this is the biggest check we can do that we've done the right thing, because you can get the same information independently from polarization and from temperature. And the fact that they agree so well is incredible. What you normally do is you calculate the best model for temperature, and then you map that onto polarization and vice versa, and you see it's the same model. So then when we actually give these numbers, we take the information from temperature and from polarization, because why not use both if we can? But polarization, we have not yet reached the same level of precision as we have with temperature. Yet. So by now we have many, many, many different CMB experiments measuring this first light. I'm showing you here the same thing I showed you before, where you have the amount of temperature blobs that you have and the size. The top one here, that is called like CMB-TT, this is temperature. The middle one, CMB-EE, this one here, this is polarization. The CMB-BB one down here is a different type of polarization that is very difficult to measure, and that can be produced basically by ripples in the universe, by gravitational waves in the very early universe. So we have measured temperature. We're progressing with E polarization, which is this one here. B polarization is really difficult to measure. But you can see here Planck in blue. So WMAP in gray, you can see it's up here. Planck in blue goes all the way down to here. Then you have ACT, the Atacama Cosmology Telescope in green, sorry, in orange going down here. You have the South Pole Telescope filling out this part here. But then if we focus on polarization, you can see Planck did a pretty good job up to about here. And then to go further with polarization, we have two ongoing ground-based experiments. These are the Atacama Cosmology Telescope, the polarization aspect, and the South Pole Telescope, the polarization camera. The picture that I'm showing you is from 2018. It is out of date. There isn't a new one that is as pretty, and I didn't have time to make my own, but this is an out-of-date image. By now, these pink and blue ones, the error bars are like this here. So you no longer have these vertical lines here. The pink and blue ones now go down to about here with the same level of precision. And these are ground-based experiments. So this is what we have ongoing currently. This is for temperature, this is for polarization. But there's something else in the cosmic microwave background radiation. Something that we haven't yet measured, that we haven't yet been able to measure, and that could give us as much information as we've already learned from the CMB. And this is spectral distortions. Now, spectral distortions is something I have a soft spot for. I've written several papers on the topic, and it's just like one of my literally favorite things. So I want to go back to the black body spectrum. I mentioned before that this is a prediction of Big Bang. We expect this background light to be a perfect black body. Finland and COBE measured it to be the most precise black body ever. Except this is not what we predict. We don't predict a perfect black body. Our standard model of cosmology, where we have this amount of dark matter and dark energy and stars at 400 million years, within this model, you don't actually expect it to be a perfect black body. There should be differences from a black body spectrum of about 1/1 billionth. So if you could get this to 1 billionth precision of what it is, you could measure these tiny, tiny, tiny differences. And this is known as spectral distortions. This is a prediction of our standard model of cosmology. Our standard model of cosmology says if you push this down to 10 to the -9, so 1 part in 1 billion, you will see a breakaway from this black body. You will see some of these red crosses no longer lying perfectly on the blue line. 1 in a billion. But there are many other models beyond our standard model that also predict these, maybe at 10 to the -8. So 10 in 1 billion. These are models that are not our standard model of cosmology. Just let's go back. When we had steady state and Big Bang, the way we were able to tell them apart was by measuring the CMB, by measuring a prediction. Okay, now we have this model where we have cold dark matter, so dark matter doesn't talk to anything else in the universe. But you can have another model where dark matter is made of primordial black holes, which are black holes formed in the very early universe. You can have a model where the dark matter and the dark energy talk to each other. And in all of these models, you have a different amount of spectral distortions. So how can you tell these models apart if all their other predictions are the same? By measuring these spectral distortions. So measuring these spectral distortions really could make or break our standard model of cosmology and all our other theories. You know, if our standard model says you will measure them at 10 to the -9, 1 part in 1 billion, and we send a telescope to space and we don't measure them, our standard model is wrong. It is as simple as that. It is a prediction of the standard model. We have to measure it. So why haven't we? We have not measured spectral distortions yet, so why not? And the reason is a technological limitation. because these spectral distortions are a difference of 1 part in 1 billion. This is incredibly small. In order to do this, you need to have perfect understanding of galaxies, of dust in between galaxies, of basically everything happening between us and the CMB, everything that could get in the way. When FIRST launched, or when COBE First took this data here, they were able to measure, okay, it is a black body, perfect black body, up to 1 part in 100,000. So we need to be 4 orders of magnitude more precise. We need to be 10,000 times more precise than what COBE was in order to measure the spectral distortions we predict. A lot of people think this is impossible. A lot of people in the community think we will never be able to measure this. 100 years ago, people thought we would never be able to measure gravitational waves, and we have. So this is something that is in the CMB. It is there waiting for us. It is something that can prove or disprove our standard models of cosmology. What are we waiting for to do this? Of course, we need the technology. That's what we're waiting for. But there are a lot of people in the community working on figuring out how we can do this. And people ask me sometimes, like, what do I want to see in my lifetime in cosmology? And you've probably, if you see me before, you've heard me give different answers, gravitational waves, neutrinos, blah, blah, blah. But a spectral distortion mission is the next step for CMB physics. It is the next thing to measure. It is the next thing to aim for. And I don't think it's as far-fetched as we might think. And I'm not the only one who thinks that. So the cosmic microwave background radiation has already given us a ridiculous amount of information. But the story doesn't end here. Over the next 15, 20 years, I believe, we are going to get the next generation of CMB missions from the ground. So we already have the Simons Observatory, which is being constructed now. And Simons Observatory is going to be an array of, I believe it's about 10 to 15 telescopes here on Earth that are trying to measure the CMB temperature and polarization even more precisely than Planck did. Of course, because they're here on the ground, they're going to focus on a small patch of the sky and not the whole sky. CMB stage 4 is in the planning phase. It's like 20 years away. CMB stage 4, I think it's going to be about 100 ground-based telescopes all working together to stare into the universe and try to get the CMB even more precise. These are ongoing, these are planned missions. We are going to get data from CMB stage 4 and Simons Observatory. And the distance between now and CMB stage 4 and Simons Observatory is less than the distance between now and COBE. It is going to happen. Then we can talk about LIGHTBIRD. I love LIGHTBIRD. LIGHTBIRD is a mission that I have been rooting for many, many years. LIGHTBIRD is a mission that is set to launch in 2032. It's by the Japanese Space Agency, JAXA. You can see what it's going to look like here on the right. And this one is looking for gravitational waves in the CMB. Let me just recap. Let me go back to this one here. We had the temperature one at the top. We had the E mode polarization in the middle. And at the bottom, you can see this B mode one that is hard to measure. So the B mode is what happens when the CMB itself feels the vibrations of the very early universe. There could have been vibrations in the early universe produced during inflation, and these vibrations affect the whole background of the universe. And the CMB might be able to very, very, very lightly feel these. So imagine if we could get the same precision we have with temperature and with E mode in this bottom one down here, if we could fill out this part down here. And that is exactly what LIGHTBIRD is trying to do. So LIGHTBIRD is going to launch. It has been approved by the Japanese Space Agency. This is a mission that has been going back and forth for years because at some point NASA was involved and then they pulled out. The European Space Agency got involved and pulled out. And the Japanese Space Agency has funded it. It is going to launch in planned date is 2032. We can probably expect a couple of delays. There always are. But this means that, let's say it launches in 2035. It takes data. By 2040, which is only 15, 16 years away, which is terrifying to think about, 2040, 16 years away, we could have the next map, but instead of temperature or polarization, it would be seeing the ripples left over from inflation. And this would tell us if inflation happened, how inflation looked, and what it's doing. LIGHTBIRD is a next generation CMB mission, and it has a launch date. And then there's Voyage 2050. Voyage 2050 is a possible spectral distortion mission. It is not yet confirmed. It is not definitely going to happen. but NASA listed it under its long-term objectives. There was a call a few years ago where NASA give us a roadmap for the next 50 years. People proposed missions, and one of the ones that was proposed was Voyage 2050. And Voyage 2050 was one of the three main directions NASA selected. There was one for exoplanets, one for exploring galaxies, and one for potentially exploring spectral distortions. This is not a commitment from NASA to build it. It's NASA saying we are interested. Prove to us that it can work and we'll build it. So we now have the next 20 years, 30 years to prove that we have the technology for this, that we'll know how to do the science if we get the data. Voyage 2050 is not yet confirmed, but it is on the long-term roadmap for NASA, which means 30 years from now, we could have a spectral distortion mission. We could have spectral distortion data. And that will be an incredible day for cosmology. So I love Lightbird. Voyage 2050 is an incredible idea. And it's amazing to think how far we've come in the last 30 years, but how little we know about the CMB despite everything. We don't know about the BMO polarization. We don't know about spectral distortions. So yeah, we've come a long way, but this is not the end of the journey for the CMB. And there's more we can do. So this is everything I talked about today is the cosmic microwave background radiation. These are the particles of light that broke away 380,000 years after the Big Bang. But we know that 3 minutes after the end of inflation, or after the Big Bang, neutrinos did the same. Neutrinos are these tiny, tiny, tiny particles that are zipping around the universe. They are very, very difficult to measure. And neutrinos broke away from everything else 3 minutes after the end of inflation. So 300,000 years before the CMB did. What if one day we could get this map with neutrinos? What would we learn? We would get a photo of the universe 3 minutes after the end of inflation. And what if we could get this map of the gravitational waves produced in the first fraction of a second of the universe, when the universe was growing and having growth spurts and everything was crazy and weird? The universe could be filled with these tiny ripples, this afterglow of this early random period. Imagine if we could get this map, but for 1 second after the end of inflation. That is what I'm currently working on, and I did a talk, I think my first talk with iTelescope was about gravitational waves. But we've done this with photons. What if we could do it with neutrinos? What if we could do it with gravitational waves? I hope I've convinced you by now that the CMB is amazing, or at the very least convince you that I think it's amazing. So the title for this talk today was Cosmic Dawn, the dawn of light, the dawn of light. But I'd like to propose another idea. The cosmic microwave background radiation has been the dawn of precision cosmology. It is the first time we've been able to look at the universe and say, I know what you did there, up to a % level precision. It has opened the door for more precision cosmology. So the CMB is the first light in the universe, but it is also the dawn of precision cosmology. And I can't wait to see what the rest of this day brings us. Thanks everyone for listening.
Thank you so much, Deanna. If you don't mind, stop sharing, and then we can, just stop sharing.
There we go.
Bravo, really, bravo. Absolutely amazing, amazing, amazing. I don't have the words for this, and I know that everybody thinks like that too. I'm going to limit myself just to one question because so many questions are coming in. I mean, it's just so amazing and so many new things I didn't know, especially about this future journeys. I do have to ask you, one question. So if you look at the CMB map, there are some anomalies, at least from the point of Earth, that we have seen. One of them is the cold void that they seem to have, right? And another one, there seems to be an anomaly in the southern hemisphere as compared to the northern hemisphere, which seems to be slightly warmer. I didn't touch on that, maybe because it's not necessary, or maybe it is resolved already. Do you have any comments on that?
Yeah, so this is a really interesting thing, right? Because I mentioned that, we don't just look at the map, we take the statistical properties, we take the spectral decomposition, and we break it down, and we do everything there. And everything looks like what we'd expect, mostly. There's a few tiny, tiny differences. As you just mentioned, there's kind of this cold spot. So there's a region in the CMB that is, on average, a bit colder than the regions around it. And it seems to be a bit too much to be random chance. Now, the problem here is that we only have one CMB to look at. So when we say, is this a thing or is it a random, just because we only have one, we don't know if it's always going to do this or if it's just the exception. So you can always find these tiny anomalies and you can always break it down. And it's a big question of, is this just random chance or is there actually something there? The cold spot is one of those that seems very interesting, but it could equally be a random fluctuation. So it's a region that's a bit colder than others. We haven't found a convincing explanation for it, but there's a question of, do we need to? Is it that different? Is it that much of a problem that we need to solve it? So it's kind of on that region where we're not completely sure. Now, the good thing is by now we have all of these different maps. Like we have from WMAP, from COBE, obviously from Planck. We have the ones from the South Pole Telescope, from the Atacama, the Cosmology Telescope. And when you put them all together, it really does seem like what we're measuring is correct. Like the maps don't disagree with each other too much. There is tiny interesting story there about one of the maps going off a bit in a different direction, but that's fine. We think we solved that. But yeah, there are going to be these tiny anomalies. If you look at the northern hemisphere and the southern hemisphere, there's a bit of a difference. But that could also be due to how we move around things. But this is the thing, there's always more stuff you can unpick in the CMB. The cold spot, a lot of people are still working on these anomalies, are always going to be there. And they're always things that we can poke at. And I think anomalies is what scientists love the most. People think we like our data to be perfect. We don't. Because if there's an anomaly, you get to go poke at it with a stick and say, well, what are you doing there?
Yeah.
And people are doing that. There are tiny things in the CMB that we still don't understand. And maybe someday we will. But for now, we get to poke at them with a stick.
That's a very good answer. Thank you. So let me jump. So if you've got any questions, put them in the Q&A. Paul's first question, we're just going to ignore because that's what he says in the second part. So I'll read that out. Does the CMB have a range of years? Was there a CMB era that it was being emitted, or more like a quick camera flash?
That is an excellent question. Really cool question there from Paul. So yeah, it wasn't an instantaneous process. It actually lasted probably a year or two. We say that this decoupling when the photons broke away was kind of instant, but it wasn't. Because there's a multi-step process here where, the photons and the electrons didn't all at the same time decide, okay, we're ready to join up now. This was a gradual process. As the electrons and the protons combined together, this was a slow process. So some places it might have been quicker, some places it might have been slower. In regions where you have a lot of protons and electrons, it would have happened quicker. In other regions, it might have happened slower. Also, this is then related to these temperature differences. Like these temperature differences come about because of how these things weren't smooth. But this process was not instant. And this is actually something that is quite difficult to study, is like how long the CMB took to form. Because we often assume that it's instant because it's easier to calculate. Then if you change this, your results, your predictions don't change too much, but they do change a bit. And then you can have things like patchy reionization, so patchy decoupling where it happened in patches. This is also something we have to try to take into account. So it was instant in the grand scheme of things. If you think over 13.82 billion years, it was a very small fraction of that. But it wasn't like, hey, all photons are gone now. It was a slow, gradual process. And the fact that it's a slow, gradual process makes it harder to compute, but also makes it more fun to compute. And there's a lot of different approximations you can do for how that took place.
Good question. Thank you. And great answer. Richard Caputo, very nice to see you. The data is out. Yeah, the data out there is as if we are inside a balloon and it is all around us in 3 dimensions. Basic questions. How do you translate that into a 2-dimensional oval?
Love that question. So this is actually something that is called the hammerhead projection. And it is a way that we can project a sphere onto a 2-dimensional surface. This is something that we always have a problem doing because, spheres are round, 2 dimensions are not. We see this when you get the globe, when you do a 2-dimensional map of the Earth. It always looks like, Antarctica looks a lot bigger than it is. South America is stretched a lot. Greenland is ridiculously big. And then you look at it on a globe and these things are actually a lot smaller because there's always this problem of projecting things. There's other projections you can do that try to kind of smooth things out so that you don't artificially make things grow. And one of the best ones for doing that is actually this oval projection. So that oval projection really is like you have this sphere around us, you cut it in half, you open it up, and you stretch out the sphere around us. So the poles are still going to be a bit stretched, and around the edges there's a bit of this stretching happening, but it doesn't give more weight to the middle of the map compared to the top or bottom of the map. So just the edges of the map are then distorted, but the rest is mostly the same. So you kind of push all of the problems to the side. So the way you get the oval is just basically cutting it and pulling it open. And there's a lot of simulations and animations you can find online of this is what the sphere of the CMB looks like, and now here we stretch it out. And if you search for a hammerhead projection of the Earth, you can also see how the Earth would look like if we projected it into an oval as well. So it's just the easiest way to project it.
Yeah, actually, Richard's got a very good point. And I was just thinking, you've got these Jupiter, Venus, Mercury spheres of the moon and so on. I was wondering if the CMB actually exists as a globe that you can buy. Do you know that?
I have been looking for that for many years.
You have, right? Okay.
There was actually a Planck conference, one of the very early Planck conferences, where as a conference gift, because you go to conferences, you get conference goodies. Sometimes it's useful things like pens, sometimes it's useless things. But at one of the early Planck conferences, people actually custom printed these volleyballs, these beach balls with the CMB on them.
Really?
So you get this inflatable CMB ball. A limited edition just for that conference. I want one, and I know people who have one. And there was actually one hanging in my office because there's somebody in my building who was part of the Planck team, and he got his little CMB sphere, and it's actually hanging in one of the corridors in the office. So you can very much do this. I don't know why there isn't a bigger market for that, because I would buy it.
I would agree.
But yeah, I actually think the best thing they could do is make a sphere with a laser etched CMB on it. So you could actually have a tactile sphere where you could feel those tiny differences. I think that would be amazing.
Wow.
If someone wants to make a Kickstarter for that, please go ahead. I will fund it.
There you go.
Business plan.
Okay, very good. Stefan, Roger Penrose has proposed a cyclic universe that is repeatedly go through Big Bang and dark end. Yeah, would you agree with his ideas?
So there was this idea years ago of the cyclical universe, where the universe expands and then at some point it kind of runs out of steam and stops and collapses back upon itself. And this would lead to a big crunch. So you'd have Big Bang, big crunch, Big Bang, big crunch. However, back in the late 1998, people actually measured that not only is the universe expanding, but this expansion is faster than it was in the past. And you saw this in all of my figures where the universe is going through and getting bigger again. So that means that now it's a lot less likely that it's going to suddenly collapse upon itself, because this expansion is speeding up because of dark energy, or we think because of dark energy. So it seems like this collapse is now the least likely option. However, as I said, it's very hard to make predictions. We've already seen when the weather forecast is 2 days out, it's usually wrong. Making predictions for what's going to happen 1 billion years from now in the universe is not easy. What we can say is, if everything continues the way it is now, then the big crunch, the cyclical universe, is not very likely. But we can't say for sure that everything is going to continue like it is now, because we've seen that now dark energy is more important than it was a couple billion years ago. So maybe in a couple billion years, the universe might behave differently to what we currently expect. So this is what I meant by the kind of trick question I put in the poll, that the CMB can't tell us how the universe is going to end, but it can make these best guesses based on what we've seen. So while the cyclical universe was kind of nice, because then it feels kind of philosophical that it grows and collapses, unfortunately the data just doesn't seem to favor that model anymore.
Interesting, thank you. Good question. Okay, Julian Allen is asking, you say, for example, that normal matter is 4.9% of the total energy budget of the universe. What is the total energy budget and how do you measure or calculate it?
This is a brilliant question. So there's this very cool thing, which is general relativity, which is Einstein's theory of how gravity works. And this tells us that you can relate the curvature of space-time to the energy contained in space-time. So objects with mass are going to bend space-time, and the curvature of space-time is going to tell objects how to move. This is related. I know it might seem like I've just gone on a tangent, but it is related. So what you can do then is you can kind of calculate the overall energy in the universe and say, this has to be equal to 100%, right? Because we're adding everything up, so this has to be equal to 100%. So that's your total to aim for. And once you've set that, you now have an amount of energy in the universe. Okay, it's 100%. But you can use this amount of energy and map it onto the curvature of space-time, right? Because you can use general relativity. And then what we do is we say, based on the cosmic microwave background radiation, it seems like the universe is flat. So there's no curvature. So then you can have to say, like, everything else in the universe has to be equal amount of energy as we would get with no curvature. You can equate these two. So then you have a kind of idea of, okay, this is going to be the total amount. So you define something that is known as the critical density of the universe. The critical density is, what density does the universe need to be flat? And you can pull out a number. And we have this flat universe, so now you have this critical density. So anytime we talk about the energy budget, what we're saying is, we know this has to add up to 100%. So we take each component, we divide its density, which we can get from the CMB, by the critical density. And this is going to add up to 100 because we've made it so. So then you basically take the energies that each component has, or the density that each component has, which you can get from the CMB. You divide it by this critical density, which means the universe is flat, which we also got from the CMB, and that gives you these percentages. So the total energy budget, we say, is 100, because it needs to be 100%, because otherwise it wouldn't make sense. But then if you have a universe that has curvature, this changes. So then, for an example, if you add a bit of negative curvature, then you add up those ingredients and you've kind of overestimated, because you're now more than 100%, because your negative curvature means you needed it to be slightly less than 100%. So then you say this negative curvature has negative energy to compensate. So it's basically kind of a mathematical trick that we can do where we just say everything needs to be 100%, because otherwise, math doesn't work. And then we take the densities that we get from the CMB, we normalize them to this 100%, and then we get the fractions. Does that answer the question?
I think it does. It's very well indeed, very well.
As always, if something is not clear, you're all welcome to ask follow-up questions.
Yeah, and Stefan is asking more about the early plasma here. I think it's very likely that at the time of the Big Bang, the light intensity has been very enormous, and it's well established that in laser technology that very high intensities generate two photon effects. Yeah, the measured intensity is likely a mixture of one photon emission and two or more multi-photon emissions. Is it true? If true, this will modify the interpretation of the CMB maps, is his opinion.
Yeah, so that's a really important thing to address, actually, and it's a really cool question. So I think there's a slight problem here that you're thinking about the CMB being emitted from something, being produced from something, which is what we have if you make a laser. You're producing this beam of photons, you're concentrating it and sending it out. If I turn on a flashlight, I'm emitting light. But the CMB, these photons were not produced via an emission process. These photons were already there in the universe. They were left over. Actually, these photons were produced in the very early universe when particles and antiparticles annihilated. They produced these photons. So it's not that these photons were emitted at the time of the CMB. It's that they stopped bumping into everything else and they could move freely. So we actually often refer to the CMB itself as the last scattering surface. So the surface in the universe at which the photons last scattered off of something else. So it's not so much that the photons were emitted, because if they were emitted, then you could have this process of them being emitted in different ways. It's that the photons were there. They just couldn't travel because of all the other particles. But once the protons and electrons had combined together, the photons could move freely. So it's not so much a continuous emission process, but more that the photons can then move freely throughout the universe.
Yeah, maybe my understanding, at least as a physicist here, from Stefan's point of view, is probably when the universe was much hotter. If you have where atoms were not bound, you had electrons and protons, and they would bump against each other. They could actually produce a photon, and they could be multiple photon processes at higher temperatures, which once the atoms formed, you don't have that anymore because the universe is transparent and you more or less have an equilibrium of photons, something like that, right?
No, this is very true. That when I say these photons are bumping into something, what is actually happening is they're being absorbed and emitted at the same energies. And you are actually right that this is something we do need to take into account. So this is something that is a minor correction to our recombination history. I mentioned before that this process is not instant, that it takes place over a span of a while. So another factor that we need to account is, for an example, where you have 2 electrons in an atom, that changes how things behave. So this is something that goes into our reionization calculations or our recombination calculations. It's called recombination, but it's actually the first combination of photons and electrons. So it is something that we need to take into account, but it is a subdominant effect, because if you consider here that you're very right. My first answer was a bit scattered, but yes, thank you for helping me focus that answer there, Christian. Yeah, so it is something we do need to take into account. But if you consider the way, the overall energy of the CMB, it being emitted once or in a 2-step process doesn't really affect the overall thing. So if you have something that bumps off twice rather than once, it's not going to change the overall behavior of the CMB in a meaningful way. So it is something that we need to take into account when we're doing this slow recombination process. It is something that goes into the calculation, but it's not something that has a dramatic effect. But you are very right that it can be seen as a continuous emission and absorption process.
Yeah, great question. Thank you. Okay, Richard. With the fairly recent discovery of gravity waves, did the flat universe concept gain or lose credibility? Is there a simple answer? Wow, here we go.
Love the question. Yeah, so gravitational waves are my second favorite thing in the universe, and they are these ripples in the fabric of space-time. So if you think of space-time as being this kind of sheet and objects within it distort space-time, gravity waves are kind of these ripples. Like if you're in a swimming pool and you move about, you create ripples in the ocean or in the swimming pool. Gravity waves or gravitational waves are these ripples in the fabric of space-time. Now, because they're kind of embedded within space-time, they can't actually tell us about the overall shape of space-time. So when we say that the universe is flat, this is on average over the whole universe, right? Because we know that close to a star or close to a black hole, the universe is not flat. There's the curvature of space-time. So when we say the universe is flat, it's averaging over everything. Gravitational waves don't really care if the universe is flat or curved or not. They're still going to travel. And they don't really give us any insight into the shape of the universe. So gravitational waves are great for measuring. The gravitational waves that we've measured so far are from black holes smashing together, which is a cataclysmic event. And the ripples that reach us tell us about how this took place. They don't tell us so much about if between the black holes and us, there was any type of curvature. So the discovery of gravity waves, which was an amazing discovery, by the way, didn't really add or take anything away from the flatness of the universe. And I did say the universe is flat, and that's what the CMB tells us. I should mention that not everyone is satisfied with that answer, because if you break the CMB data into different chunks and take different chunks of it, you don't always get that the universe is flat. There's a lot of interest in the universe not being flat, but it seems like all of the data points towards a flat universe, but there is still a bit of wiggle room where you can have perhaps a tiny curvature, and that's what people like playing about with. But gravitational waves do not really tell us much about that.
Now we're getting also an inflation where more questions are coming in than you can answer, so I have to be a little bit conscious of your time if you're still on.
Yeah, it's fine. Okay. It's a CMB, I can talk for hours.
They're just so interested, and I can't blame them. So, Mark, super presentation, absolutely.
Thank you.
Given everything we've learned, what can CMB do to assist in decoding dark matter and dark energy? Yeah, and what does that mean to us?
I love this question because this is literally what I spent my entire PhD working on. Okay. So, we have the CMB spectrum, and of course it's measured really, really precisely. But there is still a bit of chance for wiggle room. You can still get a few things there. So a lot of what I asked during my PhD, the question I try to answer is, what happens if dark matter is actually not as cold as we think? What if dark matter could talk to other particles just very, 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 very slightly? And then you can take the CMB and you can say, okay, if dark matter is bumping into baryons in the early universe, it can only do so this tiny amount, because if it was more than this tiny amount, the CMB would look different. So that's something that the CMB can help us show. So we can use the CMB to kind of narrow down the properties of dark matter and dark energy. What we usually do is we ask these fun questions of, can dark matter do this? And usually the CMB is like, no. Can dark energy do this? And the CMB is like, nope, sorry, don't like it. But then there's some other things that you can look at that are not just the CMB. So there's other things in the universe you can use to study dark matter and dark energy. But the CMB has already killed a lot of extra models. There's a lot of stuff that we thought we could do and then we can't do. But what we can do going forward with the CMB, if we get more polarization data, we can get more information about, could dark matter talk even very slightly to other particles? Polarization data is going to help push this down. And if we get spectral distortions someday, we can answer the question of, is dark matter made of primordial black holes potentially? We could maybe ask the question of, could dark matter decay into standard model particles in the early universe? Could dark matter annihilate? So you have dark matter and anti-dark matter, they come together, they produce standard model particles. This would produce spectral distortions. So given everything we've learned about dark matter and dark energy, which is a lot, the CMB has told us a lot about dark matter and dark energy, but there's still a lot more it could tell us, because we don't know what dark matter is. We don't know what dark energy is. We know what it does, but we don't know what it is. And the more precisely we can measure the CMB, the more we can play about with this. So I showed you that blue line before that goes through all of the data points. That is our best model. But you can always add more things. That is our best model that only actually has 6 numbers in it. But then you can say, what if I add a 7th number, which is dark matter mass? Or what if I add an 8th number that is dark matter bumping into something? And usually the CMB tells you like, oh, this doesn't improve anything, so why bother? But as we get more and more data, you can try with more and more of these numbers to see what's going to happen. So there's still a lot we can do with CMB and dark matter, dark energy going forward.
Very good. Thank you, Mark. Stefan, okay. You got another question, but
yeah, but it's light and light. But I have to answer this question.
Okay. Do you want to answer it? It's about light.
Okay. So the question: when LISA will be launched, will LISA give different data from LIGHTBIRD? Yes. And I love this question, and the answer is yes. So LIGHTBIRD is looking for gravitational waves in the CMB itself. So these are not directly gravitational waves. What it's looking for is how the CMB reacts to fluctuations or vibrations in the cosmos. So the type of vibrations that LIGHTBIRD is looking for are the ones produced by inflation. So there's this dramatic period of exponential expansion during which the universe is stretched, and we're kind of looking for the stretch marks of inflation. And this is something that would then leak or have an effect on the B polarization of the CMB. And that's what LIGHTBIRD is going to measure. So LIGHTBIRD is very much targeting inflation. LISA, on the other hand, is looking for gravitational waves coming from a bunch of things, like supermassive black holes smashing together, small black holes falling into big black holes, a lot of stuff like that, and also what happened after inflation. So what I work on is the question of a fraction of a second after the end of inflation, the universe was still going through a lot of changes. And depending how these changes happened, you could have produced gravitational waves. So if LISA is able to measure these gravitational waves from after inflation, but still from the first fraction of a second of the universe, it will tell us how we went from inflation to CMB, like what happened in that in-between stage. So LIGHTBIRD is very much focused on inflation. In fact, the I in LIGHTBIRD, so LIGHTBIRD is also an acronym, but it's an acronym for something that is 2 lines long, which is why I didn't bother reading it. It is like the light mission something, 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 but the I stands for inflation. Right. So LIGHTBIRD is very much focused on inflation, whereas LISA is focused on a lot of astrophysical sources of gravitational waves and also what happened after inflation. And that's what I work on, what happened after. Now, I used to work on CMB, now I work on gravitational waves with LISA. But they will definitely be complementary data sets. So they tell us different things, but it will be good to have both.
Interesting. Thank you. Richard again, if spectral distortion blows the standard model out of the universe, what alternatives to the standard model are being considered?
Yeah, so just to specify the standard model, I've used it today, and anytime I say standard model, I'm talking about cosmological standard model, but there's also the standard model of particle physics, which I haven't touched upon. So let's just specify that I'm talking about the cosmological one.
Right.
So the standard model is this one where you have three ingredients: dark matter, dark energy, normal matter. You know these percentages. That is our standard model. If we look for spectral distortions and we don't measure them, then we need something else. For an example, could there be a fourth ingredient that we've overlooked? Could dark matter and dark energy talk to each other? Could dark matter be made of primordial black holes? Could dark matter bump into other particles? All of these things produce a different amount of spectral distortions.
Or a multiverse? I don't know.
I don't think so the problem with the multiverse is it doesn't directly impact the CMB, which is where we need the spectral distortions to happen.
Okay, I see.
So unfortunately, but yeah, if we get rid of our standard model, then we have to look at something like, do we change the dark energy part? Do we change the dark matter part? Which part of our standard model do we have to change? But the thing is, the part of the standard model of cosmology that gives us these spectral distortions is the way the photons and the initial protons talk to each other. The way they talk to each other, the way these broke away, this in itself produces these spectral distortions. So then if that is wrong, we have a big question of how do we explain the CMB, but not spectral distortions? So I think what's much more likely to happen, hopefully, is we'll either measure exactly the amount CMB predicts, exactly the amount our standard model predicts of spectral distortions, or we'll measure more than we expect. And if we measure more than we expect, then we get to add things on to our standard model, like maybe dark matter talking to other particles. If we don't measure them at all, now that's a problem, because then our whole standard model is wrong. So if we measure the wrong amount, we can kind of add things onto it to other extensions, other behaviors of dark matter or dark energy. But if we don't measure spectral distortions at all, my first thing would be, did we mess up the experiment? But if we consistently do not measure them where we expect and keep pushing it lower and lower, then we have a problem. And then we go back to the drawing board and we figure out the new model. And that would be very fun.
Great answer. Thank you. And great question, Richard. Really very nice. And this time, Richard Drenner, follow-up. Thank you. Your discussion of, okay, that's
answered
fine.
the question. Excellent.
That's great. Okay, Natalia, does the CMB map change in time? Will it look differently in 1,000 years?
Yes, it will. So this is a very fun answer. There's very fun question, because as the CMB photons are being redshifted, they're gradually changing. If you wait long enough, they will be redshifted so much that you won't even see them. So for an example, 10 billion years from now, people will not see a CMB. And we're actually quite fortunate, because if we'd done these measurements of the CMB, I don't know, a couple billion years ago, then the CMB would have been still in the wrong range, where we wouldn't have been able to measure it as microwave. We might have measured it as radio waves. We might have seen it as something else. So it is gradually changing. And there's a very fun question that when I was the teaching assistant on the course of advanced cosmology, where the students learn how to actually calculate everything that goes into the CMB, which Christian and I were talking about just before we started, right, with these complicated equations. So the course where we teach that to the students, someone asked me in one of my live streams at some point, does the CMB look different over time? And that inspired us to ask the students that question as an exam question. Calculate how long we have to wait to see an entirely different CMB map. Wow. And it's something you can calculate. And we set this as an exam question to the students based on someone asking me this exact question. The answer is about 10,000 years. So in about 10,000 years, it wouldn't look completely different, but it would look different to today.
In that small range, 10,000 years?
Yes.
Oh.
Like not completely different,
yeah,
but you would see some differences. Enough that you could see some differences, yes.
So you're saying that maybe the Egyptians saw a different CMB if they could have measured it?
If they could have measured it, it would have looked very different back then than it does today.
Isn't that interesting? Thank you for that.
I love that question.
Yeah. Ashley, how are the time frames that are given for certain phases of history of the universe determined? Specifically, more the time frames around the time of inflation.
Yeah, so that is a great question. There's something that I've been kind of vague about, which is the fact that we don't know how long inflation lasted. we usually think of inflation as being this quick process. But inflation deletes the memory of anything that came before it. Inflation could have lasted 10 billion years. It could have lasted 1 second. It could have lasted somewhere in between. So I always try to say after the end of inflation, because that is actually when we can actually start our clocks. Anything that happened before inflation, we don't know. But then the time frames for things after that. So my last iTelescope talk that I did last year was called the first 3 minutes of it was about like the first 3 minutes of the universe. And I went through very precisely the timestamps of when different things happened. And the way we know this is by figuring out what particles look like or how particles behave at different energy levels. So if you increase the energy, you get different behavior out of things. And if you go back in time and you believe the Big Bang cosmology, which we've seen today we should, as you go back in time, you go back to higher energies. So then you can map these energies onto different behaviors. So you can say, for an example, at some point, at some specific energy, particles and antiparticles annihilated. A bit of a time later, some forces broke away. A bit of a time later, the neutrinos broke away. And all of this, you can take your standard model of particle physics, you turn up the energy, and then you turn it up to the energy that we had in the early universe, which we can calculate with the Big Bang, and then you can tell the story of what happened. And along the way, there's different benchmarks that you can measure, like 3 minutes after the universe, after the end of inflation, this process would have happened. This is how we might be able to someday measure it. 380,000 years after the end of inflation, photons broke away. Today we have the CMB. So we have these different kind of lights along the road that guide us, but the general journey is set out by the standard model of particle physics turned up to high energies.
Yes, good. Okay. John comes with an interesting point again. So the 3 normal dark matter energy percentages are derived from a snapshot of the early universe. So that's what the distribution was then. Is this distribution unchanging, or would it evolve in subsequent 5 or 7 billion years? Is there a way of examining that it might be now, if it might be changeable and so on?
Yeah, so it does change. It absolutely changes. The numbers that I always quote are the numbers today, not at the time when the CMB was produced. So you take the map of the CMB, we put so the good thing is we can calculate very, very precisely what should happen. Like if the Big Bang model is correct, you can very precisely calculate how everything evolves in the universe, how everything behaves. We know how matter dilutes in the universe as the universe expands. We know how dark energy dilutes throughout the universe as the universe expands. And this is something we can calculate. So what we do is we use a CMB to get what the universe looked like 13.5 billion years ago. And then we say, okay, based on what it looks like then, and based on Big Bang cosmology and standard model with these components, make things evolve. And then you play the movie forward until you reach today. So all of these numbers that I give are the values today, not the values at the time of the CMB. At the time of the CMB, you basically didn't have much dark energy per unit volume of the universe. What dominated at the time of the CMB was actually dark matter. If you go back a bit further back in time, what dominated was normal matter. But because we know how these different ingredients spread throughout the universe, we can actually kind of take the CMB and fast forward it to what it should look like today. And that's how we do it. We project it forward. And it is a pretty good projection to our knowledge. Of course, then you can find some small things that might say, okay, maybe we're very, very slightly off. But assuming Big Bang and standard model of cosmology, we can get the numbers today based on what they look like at the end of the time of the CMB.
Yeah, and just adding on to that, but so if you can actually go back in time, why can't you go forward in time? Because you said your model doesn't predict the future. I mean, there must be some type of window of future.
Sure. So at this point, we can make predictions, right? We can say, okay, based on what it looks like today and how things evolve, this is probably how it's going to evolve.
Yes. Okay.
But that is based on what has happened up till now. So how far into the future do we evolve this and still trust it?
Yeah, right. Good answer. Okay. Richard, just for fun.
Richard again.
Yes, that's another Richard. There were 2 Richards, right?
Ah, 2 Richards.
Yeah, there are 2 Richards. Yeah, that's right. But Richard is a big name today, just like the void or something. I don't know. Just for fun. if you had a 5-minute conversation with Mr. Einstein, what questions would you have? Yeah, oh, that's a great one. Would he be upset with flat universe?
I think Einstein would be okay with flat universe because, you know, it fits in with his with his general relativity. I actually don't really know what I would ask Einstein because I always find that, you know, science is not about individual people. Science is always a collaborative effect. Of course, Einstein is the one who came up with general relativity, but there are a lot of people who contributed to that theory, to that model. And I don't feel like having a conversation with Einstein would be any more illuminating to me than having a conversation with hundreds of other physicists who I get to speak to on a regular basis. Of course, he had very good insight into a specific part of the universe, which built on other people's works as well. But I always find these questions like, what would you ask this one specific person? I'm never really sure, because it's like, if I have a question about physics, I go and talk to people who study these things today, and we discuss them and work them out. Yes. So I'm not really sure of like pressing questions that I feel like I need to ask any scientist. You know, if I'm going to be controversial, I would maybe be inclined to ask Einstein how much his wife actually contributed to his work, which is often not talked about, but his wife did actually help him with his work, but is never mentioned. So perhaps if I was feeling controversial, that's the type of question I might ask. But I don't feel like I would gain any deep philosophical insight by having a conversation with one specific physicist. But, you know, I know a lot of people will answer this question differently.
Yeah, okay, good. And Timo's asking something about the dark age or dark period.
Nice.
Photons have just been released. First stars were not born, but should have been a great glare of the Big Bang. Yeah, it's a question.
Yeah. So there is this Big Bang, but these photons have now stopped interacting with anything else, right? They've broken away. They're doing their own thing. So anytime you actually like measure light is when a photon interacts with something else. Like when we look at light, the photon is interacting with our eyes. So in that period, there's kind of nothing going on. The photons have broken away. They're traveling. They're doing their own thing. So there's no new light. There's nothing that light can bump into, because at that point, the universe is full with hydrogen atoms and photons. And the photons are no longer talking to the hydrogen atoms because the energy has dropped when they broke away. So there's really nothing for these photons to do. So they're just traveling, doing their own thing, which means that they're not producing any new light that we can measure. Those photons are the ones we then measure today. When the first stars turn on, what you get is these new photons injected into the universe, and these new photons are going to be more energetic than the CMB photons, which are just doing their own thing. So when the stars turn on, you get this kind of new light that is more energetic, and then that light can start interacting with other things, and then you can measure things again. But between the CMB and the first stars turning on, there is nothing in the light range, but there are still these photons, and by that point they're kind of into the radio frequencies, which means if you could have an incredibly precise radio telescope, you could actually try to measure what happened in the Dark Ages, and that's what we're trying to do. This is called 21 centimeter astronomy, where you try to look for interactions at a specific length of 21 centimeters, which is in the radio range, and that would help you understand the Dark Ages.
Yeah, that's neutral.
Yeah, exactly.
Yes.
Exactly. Before the stars reionized everything.
Yeah, interesting. Yes. So if we look for aliens and so on, we look for the 21 centimeter line. Everybody seems to understand it, right?
Yes, exactly. Just, you know, turn on radio telescope, see what we hear.
Okay. Michael, since we've been looking at the CMB with high resolution for several years now, is it absolutely stable? Yeah, well, it's a good question. Here you go. That's the similar question again. Yeah,
this is very similar to what we answered before, right? Of how long do you need to wait for the CMB to change? You need to wait at least a couple thousand years, probably 10,000 years before you notice any changes. So the only real difference between COBE and Planck has been our technology has progressed, our understanding has improved. But the CMB itself shouldn't have changed in between that time. And it doesn't look like it's changed. Within some statistical uncertainty, it's the same.
Sure, but if you had this incredible, you measure the spectral distortion of a black body, if you had this resolution, you might be able to see it much sooner when changes, right? So, okay, that makes complete sense. Gary, is there any information basis or meaning being shown by the orientation of the short random looking lines are shown in the CMB diagrams. Okay.
Yeah, so I think in this one you mean the polarization map, I guess, where we had these lines.
Yeah.
So these lines do actually have a deeper physical meaning, in the sense that there's only really two ways photons can vibrate. They either have vibration in one direction or in another. It's basically, you can draw it as either a circle. So I'm just going to very quickly do a sketch here. So if you imagine, you can either draw it as something, hang on. So if you draw the lines, you can draw them as something like this, where you either go in this direction or like this, a circle around something. So you can imagine in each case, the photon is kind of traveling towards you through the center here. And these are the two ways we usually represent the polarization. So they can be a mix, they can be something in between. So those lines are showing you at each point kind of which direction of polarization we have. Because there's only basically two possibilities, then you can break it down into a sum of these two. So any point on that map is going to be something like that. So there is a deeper meaning. The physics behind it is actually really cool, but requires a lot of like optics and polarization, which would take me a whole other talk to talk about. They're next year's topic.
Next year, good. Okay, very good. John, can we reverse project the point of the origin of the universe center from the expansion?
Love this question. Love this question. This is actually a common misunderstanding with the Big Bang. So the Big Bang is a very bad name, because the Big Bang kind of implies there was a big bang. There was something that banged. There was an explosion.
That's right.
But that's actually not the case. The expansion of the universe took place at every point in the universe at the same time. So it's not like I'm here and everything is moving away from me. It's like wherever you are, everything is moving away from you. So there isn't really a center of the expansion, because it's not moving away from one point. It's moving away from every other point. So you can define a center. This goes back to what I mentioned at some point during the talk, that the universe looks the same in every direction from wherever you look. There is no privileged place. What we see and what someone a few billion light years away sees should be exactly the same, because we don't occupy a privileged spot. Nobody does. So then there's no center. It's really not the center of an expansion, the center of an explosion, because there was no explosion. It's every point in the universe is the center of its own expansion. So the reason the CMB is a sphere centered around me is because I'm at the center of my own sphere of expansion. Someone on a planet a couple billion light years away would actually see a different CMB, but they'd also see it centered around themselves. They'd also see this sphere with themselves at the center, because we are at the center of our own expansion, but everyone in the universe is at the center of their own expansion. So
yes.
There's no point that we can say, here, this is the center.
And okay, this is again probably similar to the questions before, because it relates to the change of the CMB, right? Turns to CRB, which is probably radio, and then CIB is probably infrared. I'm not quite sure.
I guess so, yes. Fun fact, the cosmic infrared background is actually something we have to deal with when measuring the cosmic microwave background. And it's one of the dusts that we need to get rid of. It's one of the things that we need to clean out. So that is a thing, but it's not the same thing. But already at the dark ages, the CMB was in the radio range. So the infrared one would have been before that, right? So already, if you think that as the universe expands, it's not kind of linear, you have this exponential expansion. So not exponential, but you have this expansion that is not linear. It's why when we talk about temperatures, it dropped dramatically at the beginning and then gradually afterwards, right? It didn't linearly go down. It dropped dramatically and then gradually went down. It's the same with the redshift of the photons. It went down dramatically at first and gradually flattened out. So the cosmic radio background was already at the dark ages, and the infrared one would have been before then.
Yes. Oh, good answer. Samaj is saying, is time a fourth dimension object in the cosmic ocean from the emergence of the Big Bang to today, or is it some different object?
It's an interesting question. What is time? Is time an actual object? Is time a concept? Is time just our way of making sense of the universe? It's not a question that we can really answer unless we go to entropy. So entropy is second law of thermodynamics, entropy always increases. Entropy is kind of the state of disorder of a system. Entropy gives us an hour of time. If I have a coffee mug and I throw my coffee mug on the floor, there is a clearly defined first state and second state. I have coffee mug, I have broken pieces on the floor. You have point A, you have point B. So this gives you a time direction between them, right? You wouldn't expect the broken pieces of a coffee mug to spontaneously assemble into a normal mug because of entropy, because of adding to chaos. There's a billion ways I can break that coffee mug. But assembling that coffee mug to be that exact mug as it was is statistically impossible. So entropy gives us a direction of time. So this is probably the most physical interpretation we can have of time. It tells us how you get from event A to event B. So time we counted as a dimension because to tell us about anything in the universe, we only need 4 coordinates. We need space and we need time. So if I told you like 2 trains are on a train track going in opposite directions, are they going to crash? You don't know because maybe one's doing the journey today and one did the journey 50 years ago. So you need the time dimension to make sense of things. So we put time as a 4th dimension because it's one of the 4 things you need to specify what is happening at any given time and place. But from a more physical perspective, you can say it's how you get from event A to event B following the hour of time. But then you can get philosophical of what is time? Is time subjective? Einstein told us that time is relative. So I feel like there's a lot of different ways one could answer that question. But there's my take on it.
But just adding some fun fact, which I found so interesting, is that there's a limit to time too, the Planck time, right? It's like 10 to the minus 4 or something crazy small, right? So it does. Okay, we're nearing the end. I'm sure you're tired.
Getting to the end.
Yeah, Ziv has James Webb discovered younger galaxies than expected. Oh, I see. Is this a contradiction to the CMB?
Yeah, that is a very cool question. So the JWST telescope is finding galaxies that are a bit younger than expected. And while this is not in direct contradiction with the CMB, it's not what we expected based on the age of the universe and our understanding of how galaxies form. Now, there is the caveat that we're a bit fuzzy on how galaxies form. It's still a process that we haven't completely understood.
Right.
Now, there's a problem that these galaxies that JWST has found, there's enough uncertainty with them that there's a lot of other questions I think we need to answer first before we say, okay, our cosmology is wrong. Like, have we fully understood how light behaves on its path from that galaxy towards us? Are we properly taking into account things like lensing effects, where you might have a clump of dark matter affecting how we're perceiving this galaxy? So measuring times of specific objects or ages of specific objects is always very, very difficult. JWST does seem to have found a few galaxies that don't fit with what we expected, but it's still early days. I think we're not yet ready to say, okay, cosmology is wrong, let's restart things. It's definitely curious. And there's a lot of people working on trying to figure out what does this mean. We're not yet at the stage where we need to say like, okay, time to redo things. But it is definitely something to keep an eye on. And I think over the next few years, as we get more data from JWST, it's going to be really interesting to see how the age of these galaxies fits within what we already know.
And Max, nice to have you here. Wonderful talk, I would agree. Is AI making any difference to your work? That's a great question. So about your computation.
Yeah, so I think I'm going to make a comment that we're not yet at the stage where we have artificial intelligence. What we have are basically glorified chat predictors. But we do have these really cool like large language models that are able to calculate things and predict things. And we do have these machine learning techniques that are improving calculations or just helping people do calculations. But the type of calculations that we do to get the CMB are incredibly precise. And they also don't take that long. Once to get that blue line going through the CMB, takes less than a minute. I can run it on my computer. I can run it locally.
Wow.
I don't need to spend a huge amount of effort training a computer to give me an answer that I wouldn't completely trust. So I think there are a lot of places where machine learning techniques could be applied in cosmology and astrophysics. I think CMB calculations is a bit harder because of the level of precision that you need, because there's always going to be people who are not going to trust it. I think a good place to use machine learning is like classifying galaxies, where that's what it's really good at. Is this the right shape? That said, there is progress being made. I mentioned this code at some point that we use to compute the CMB that does this calculation, that is called class. A couple of years ago, some of my colleagues put out ClassNet, which is based on neural nets. And the idea there is that you can every time you run the code, you add it to a training database in the background, so that then when you do it in the future, it kind of checks: do I already have this one in stock? Can I already answer this, or do I need to recalculate it?
Mm-hmm.
And it's done in a way where it takes into account the limitations of neural nets and machine learning. And if the neural net can't provide the answer, it calculates it the conventional way. So that is a place where people are making progress. But I think personally, I'm not yet using any of these, and I don't see a clear direction where it would make sense to use them in what I'm currently doing.
But I do see where Max is coming from, because I mean, they're used a lot in image recognition and so on, and we can see patterns we couldn't see before. So maybe he's coming from the point of view, if you just take the CMB and you know nothing, is there anything particular that we could recognize there, maybe, and work backwards, like backward propagation that you do in AI or so? Maybe you could find something. I think that's probably his point, right? So
yeah. I think it's a thing that we've stared at the CMB for so long now, and we've done every possible calculation, that trying to find something we've missed. Of course, it would be good get an AI to look at it. But then it's the thing that we don't look so much at the images themselves, but at the statistical interpretation of the images. So then it's a question of I think using machine learning makes sense when it speeds up the process for us, or when it can do it better than a human can.
Right.
But if it can't, it might not be worth the energy investments.
Right. Okay. Now we've really tortured you enough. You've been absolutely wonderful. So Richard ends with an appropriate comment. I'm going to read that out. You should ask Einstein a question. Maybe you can ask him if he likes avocado. Let's end it with that.
Yeah, that is good. I always ask people what food they like, because then you can really, that is actually like a cool question to ask people, because then they recommend restaurants to you, and I love getting restaurant recommendations.
There you go. There you go. Deanna, thank you so much, Dr. Deanna Hooper, and thank you everyone for this incredible webinar that we've had. Thank you for all your contributions, and it's been a wonderful start in February. And Deanna, lots of success with everything. We'll see where you are next year. We talked about
where I am next year. Yeah, and if I can just very briefly mention to everyone that if you like asking me questions, I have a dedicated YouTube show for this called Cup of Cosmology. Yeah. If you just Google Cup of Cosmology, you'll find me. And I basically do this on a weekly basis and answer any questions you will have, CMB or not. So feel free to check me out.
What channel is that? It used to be Periscope and so where are you on now?
It's YouTube now. YouTube and Twitch.
YouTube,
so both YouTube and Twitch, Cup of Cosmology. Also, you can go to cupofcosmology.com and find it there, or just go to youtube.com/cupofcosmology.
And it's highly recommended, as you know. Thank you so much, Deanna. Have a wonderful weekend, everyone. Thank you for your participation. Okay.
Have a great week, everyone.